So just a reminder to keep your phones and computers muted at all times during the webinar and to save all questions until the end. If you'd like to put them in the chat box, we can address them at the end of the webinar. So as everyone knows, we are the IAC program. We have 31 universities across the country, and our field managers are at Rutgers Case. We host these webinars that are run by students, faculty in the program, as well as other companies that are connected to our program. So they're for students and by students a lot of the time. Today, our presentation will be about 30 minutes long, followed by a 15-minute Q&A. And as an update, next in 2 weeks, we'll be having our second November 2020 webinar about the performance of closed-loop Venturi aspiration aeration systems presented by the University of Alabama. On today's topic, presented by Landon from the University of Utah, the Intermountain IAC. He was one of our 2019 Student Research Award recipients, and he will be presenting on the real-time optimization of multi-cell industrial evaporative cooling towers using machine learning and particle swarm optimization. So Landon, I will pass it over to you.
Excellent, thank you. Go ahead and get my screen share working here. Alrighty, and then I think we are, see if I can pull up the chat window too. Perfect. All right, well, as Kelly mentioned, I'm Landon Blackburn. I'm a PhD candidate at the University of Utah and have Dr. Cody Powell, who is both my PhD advisor as well as the director of the IAC here at the University of Utah. So yeah, I'll be talking today a little bit about an interesting project we got into as part of was spun off from an assessment recommendation we had for one of the IAC visits. So some quick background about the nature of the energy system and the energy portfolio in the United States. This is from the Energy Information Administration, some data right here. The renewable energies are becoming a much larger fraction of our energy portfolio, which creates some very interesting challenges from an engineering standpoint. And I would go so far to say it's implementing these renewables in a way that maintains grid operation is one of the major technical challenges we have in this generation. And so all the numbers point to us just getting more and more of these, and they have some interesting characteristics to them. So this is what we call the infamous duck curve. This is from the same source here. This was several years out in California. How they get the duck curve is it's a net energy demand profile. So once you've taken the amount of energy that's needs to be generated and you subtract away all the renewables, this is basically what you're left with is a graph of how much you need to produce with the non-renewables in order to balance the grid. So you can see here as we progress through time, each year we get bigger and bigger. I guess the belly of the duck here gets more exaggerated. So you get these steep ramps that need to be met by the collective powered stations and generators you have. And those are very difficult because it puts a lot of strain and makes them a lot less efficient. And in some cases, they're maybe not really designed to be ramping that fast, but we've modified them to do so. So this is mostly met by natural gas plants, but an interesting development in the last few years is a lot more coal-fired power plants have been jumping on board with this particular mode of operation, where rather than doing what we call base load energy production, they start doing load following, where they're given a profile they need to meet, and they increase and decrease their electrical output in real time. So in case you're wondering why it's shaped like a duck or shaped like this big divot here, we get a lot of solar energy in the middle of the day, and we got a lot of wind energy at night. but some of the highest demands are right in between those peaks here in the evening. So that's one of the struggles. We haven't really figured out how to do large scale storage on the grid level to be able to fix that. So the power stations just have to be able to make do with getting over that bump every day. So there's two main categories to mitigate the duck curve and make it more manageable. There's supply side management and demand side management. Supply side management really boils down to making the power stations and the electricity producers more efficient so they can better handle these ramping situations and still be economically viable and conserve resources. We haven't really figured out the storage solution, although that would fix this as well. On the demand side management, this is probably what a lot of the IAC recommendations boil down to. Better equipment scheduling, using either thermal or electrical or other types of storage, and then upgrading to more efficient equipment. Basically trying to flatten the curve, per se, of the electrical demand so that the electrical producers don't have to do as much ramping. So this particular project we got involved with is more on the supply side of this. We were doing an assessment at a coal-fired power plant, specifically looking at their water treatment system that was attached in with their cooling tower. And it was maybe a unique situation, but it was partially motivated by the plant had some machine learning software already installed on their boiler to help it deal with this ramping situation. The plant had previously been base load and had switched to load following. And so they were looking at software solutions to become more efficient in that. So they were curious if there was a way we could apply that to their cooling tower using some machine learning to optimize the performance as it changes from how it operates at high load to low load and everywhere in between. So this cooling tower, it supports a 500 megawatt coal-fired boiler, and the goal of our project here was to try to minimize the parasitic load on the cooling or on the power plant. Basically, this cooling tower is quite the energy hog, and all of the electricity that is spent on the cooling tower is electricity you can't put out to the grid. So I'll explain a little bit in a minute how the machine learning, the optimization tied in here. But I want to give a quick background on how cooling towers work, just so we're all up to speed here. Cooling towers, this particular one was a forced draft or an induced draft cooling tower. You basically have these large boxes that are hollow on the inside, and you have a giant fan sitting on top of them that sucks air through them. And you take the hot water that comes back from the plant, and kind of drizzle it down the side of the cooling tower. And these fans create a current that pulls air through the water and forces evaporation. That's why they're induced drift. So you get cold water falling out the bottom, and you get warm, moist air being blown out the top. And the rate at which these fans run directly relates to your temperature you get out the bottom. So if you need colder water, you can just increase the fan speed. This particular cooling tower had 12 of these cells, where you have one fan on top of the cell, and they kind of operate as independent units, although they dump into a shared basin. So I got 3 of the cells shown right here just for that, for reference. They also were equipped with what we call VFDs, or variable frequency drives, on them. These are common for anything powered by a motor, where you might need behavior besides just binary on and off. So you can turn these fans down from 100% to say 75%. You actually get energy savings that way. So that's really important that they have that, and that's a very useful tool. And in theory, you could operate all 12 of these fans independently of each other at different operating points, but they don't actually operate that way. Their current method of operation is they have a single controller that controls all of the fans simultaneously. So if you have the temperature set point is not being met in the basin, they just turn up all the fans in unison. So this was kind of our our approach here is to see if we could find a way to break up these fans and take advantage of that extra degrees of freedom to increase the efficiency of this cooling tower. So another key thing to note about this project is the use of artificial neural networks. This was our machine learning model we chose to use. So neural networks are really powerful. They're data-driven. They don't need any programmed understanding of how the physics or the underlying equations of a system work. They're also really computationally efficient when you're using them. A lot of the computation cost of them happens in the offline training phase. So before you go to actually use it, you take your data and you do a one-time training that adjusts the neural network to where it starts predicting accurately. And then you have a relatively inexpensive evaluation of that neural network to get your prediction, to get your model prediction. Theoretically, neural networks can actually learn anything with the caveats of you need all the correct inputs and a ton of data, and your neural network has to be big enough. In practice, not everything can be learnable at this point, but with our current computational and data storage capabilities, we have a lot of, we've been able to model a lot of things, especially on commercial and industrial scales. So they're quite powerful tools. As long as you keep feeding them data, they just keep getting better, basically. This is kind of the basic unit of a neural network. You have your inputs, you have nodes, and you have your output. And data flows from left to right, from left to right in this diagram. So you input data, you have values from, say, sensors or weather data or whatever information you have, maybe time of day. You put that into the input layer, and then the data flows into the node and then into the output. In between all of these, you have these unique weight values that are going to be unique to every single neural network. Is going to have its own set of weights. And the purpose of these is they multiply by each of the data as it flows along to change its value. And the point of training a neural network is to determine these weights. You also have this activation function. This is where the neural network kind of lends its name from. It's kind of loosely inspired by the way neurons work in our brain. It adjusts the signal to be kind of a almost a pseudo-binary signal where it's mostly on or mostly off, but you can get in between values if you need to, depending on how it's fit. So to get a neural network, we stack a bunch of these together. You get all your inputs, you get nodes in the middle, and it eventually spits an output out. There are a lot of published algorithms for how to efficiently train these. You notice there's a lot of weights in here, and you defined values for every single one of them. We've gotten pretty good at doing that with just out-of-the-box software. They're really, one of the drawbacks of neural networks is they can be a little difficult to understand what they're doing, in the sense that you can't really follow their logic very well. They get pretty complicated really fast with all these different weights. But so the process for making sure the neural network is going to extrapolate well on things it hasn't seen is usually just withhold part of your data when you're training it, and then you can use that testing data to prove that it should hopefully do well on things it hasn't seen before. So the main problem we're solving here, I mentioned, is we're dealing with the cooling tower, and it's maybe when it was originally designed, they weren't envisioning it doing a lot of ramping, but now it is. Here's a before and after shot of the power plant's the percentage of its capacity it's at over time. And this is both before and after it switched to the energy imbalance market, where it started doing a lot of this load following. And you can see that the ramping is fairly minimal beforehand, but it becomes very dramatic once they start doing this. So they're definitely in a new operating realm, and they have maybe less historic data on how to operate at maximum efficiency here. And this is of the entire plant, and this has an impact on every single equipment piece within it, because as the boiler increases the amount of, and the turbines ramp up, the cooling tower has to follow suit. So everything is ramping all together. So the main issue we wanted to look at here is the relative efficiencies of the fans. We took some historic data of the cooling tower fans. There's 12 fans on this particular tower we were interested in. And we looked at the average efficiency. Basically, they're all at the same operating point. How much relative energy are they consuming? We fortunately have sensors on each one of them for that. And you can see in this particular case right here, we have fan 1, 6, and 7 are very efficient, whereas fans 3 and fans 10 are not very efficient. So right here, we have obvious room for improvement because they're treating these as if they're all the same. They're giving them equal burden for this cooling, for the cooling of the water in the tower. So you could probably imagine a fairly simple algorithm here where you prioritize the more efficient fans over the less efficient fans. Unfortunately, it's not really that simple. If you look at these efficiencies as they evolve over time, this is a graph showing you have your starting at high load, plant drops down to a low load, back up, ramp back up, ramp back down. And you can see the temperature being fed into the cooling tower of the water coming back from the plant it follows that same profile. The PID controller that's controlling the fans responds accordingly. It starts out with all the fans pretty much their maximum capacity, drops down to about 50%, then up and then down. So we got a couple ramps going on here. But if you look at this top figure right here where all of the efficiencies are shown, you can see they behave kind of unpredictably when you get into these ramping situations. The particular fans that are more efficient actually change to being much less efficient in some cases. So we don't know exactly why this is. I suppose we have maybe some speculation on that. And you hypothetically could go to the trouble of doing a really advanced study, putting a bunch of sensors on here, maybe doing some CFD analysis to try and figure out why this is. We decided, though, this would be a really good application for machine learning because one thing we have a lot of at the power plant is data. So if we can throw all that data into a machine learning algorithm, we don't need to know necessarily why these efficiencies behave this way, but the machine learning algorithm can be able to predict what they will be regardless, as long as we give it the data. So in summary, this is really just a perfect application for machine learning. Oh, there we go. So to set up the kind of the problem here we're trying to solve in simulation here for the power plant, this is their control structure that they have here at the power plant. So you have a PID controller that's operating in closed loop. It feeds a value into all 12 of the fans. I have 4 of them shown here. And then before we could test this on the actual plant, we built a numerical model of the cooling tower just to simulate its performance. We managed to get roughly the same dynamics, close enough that we're confident this algorithm will translate well to the real plant. So your cooling tower spits out cold water, which is compared to a set point to make sure you're still meeting that, because the plant needs to have very consistent cold water supply to complete the steam circuit over there. And obviously, if the water is too warm, the PID controller tells the fans to kick it up a notch and vice versa. And this whole thing is also affected by your ambient conditions, as well as the power plant itself. As the power plant ramps up, you start getting hotter water sent into the top of the cooling tower. So that's going to require more cooling. Conversely, you also have, when you're dealing with, say, really humid environments, cooling towers become a little less efficient there. So that's another thing to take into account there. And we have measurements on all of these. So again, the idea is to feed this into a neural network and see if it can start predicting performance so we can use that intelligently. So we took, in order to break up these fans, we took this offset array and kind of snuck this in between the PID and each of the fans. And so these are unique values that adjust the individual settings for the fans. We intentionally chose it, rather than replacing the PID controller, we intentionally chose this so the PID controller can still maintain temperature control. And we're just adjusting the relative temperatures of the fans relative to some kind of PID value that we're currently at. In order to generate some data, we we decided to feed in just random offset values and see what happens. Since we have the PID controller still ultimately in charge of the temperature, we knew it would still be able to perform well. It would just change the overall efficiency, and we could start to give the fill out the kind of the search space for the machine learning algorithm. So once we got a bit of data, we trained a machine learning algorithm on that. We got a neural network together, and we fed it, in addition to the random values we had fed in the offset array, we also fed it ambient conditions, the power plant conditions. The only thing left out was the PID controller. It seemed like it performed better without knowing that, because it had that one lags a little behind it. So we took this neural network and used it as the objective function in a particle swarm optimization. This is a gradient-free optimization technique that works really well with black box systems. All it needs is a function it can evaluate, that it can feed inputs into and get an output. And then it has a methodical way of adjusting those outputs to be able to, or those inputs into that function to get the best output. So the neural network is predicting the power consumption our tower will have, and the particle swarm is messing around with only the fan offset array. And it's hunting around trying to find the best offset array to get the smallest predicted power output at steady state for this tower. The neural network does have a few inputs that are not under control of particle swarm. Like particle swarm can't control the weather, obviously. So there are a few of those inputs that are locked, and the particle swarm is only adjusting the ones we have control over. So the results for this were, at least for these are results for the machine learning training, were really promising. We got fairly high level of accuracy. This is a parity plot of the true values of the amount of power our simulated cooling tower is consuming versus what the neural network's predicting. You can see it has a pretty tight cluster there, maybe a little more tightly at higher values. Just by nature of how the plant operates, you end up with a few more of those than the really low values. The error was pretty normally distributed, so we're pretty confident this would extrapolate well. So by pretty much any metric, it did pretty well on this. This is a full year of simulated data we fed it, which is more than a plant would be expected to have already on hand. So here's a 70, excuse me, here's a 70-hour snapshot of this algorithm actually in closed loop control and controlling the simulated cooling tower. So you have in this middle graph, this black dashed line is your PID, which you mentioned is still doing its normal thing, controlling the temperature. But we have 3 different fans here just to keep this from getting too busy. They've been added in to show that they're all being moved around at each time step by this machine learning-based optimization algorithm. You can see the temperature control is pretty well unaffected. I don't think it's actually visible here, but the actual outlet temperature of the tower is perfectly on top of this set point right here. And these other values are your tower, your return temperature coming back into the top of the tower, and your ambient temperature. So even with those fluctuating, we didn't lose any control of the cooling tower temperature, which is a key metric here. We want to save power, but we definitely don't want to disrupt operation at this huge boiler. And the blue line is our optimized versus the current practice, where basically all of the entire offset array is set to zeros with no optimization. And you can see we were able to outperform it, or at the very worst case, match it at every single time step. So very, very promising results there. If we take a look at the entire year of, we did a year of operation data to test this out. Since it's a simulation, we can compare apples to apples with exactly the same operating conditions, which you can't always do in the real world. We can see that the blue data, the optimized case, we're on average way below the current practice. You start to lose your benefit to this optimization as you get closer to maximum capacity, which does make intuitive sense if you think about it. The main advantage we're taking of here, or the main thing we're taking advantage of here, is the the room to adjust the relative speeds of these fans. And as you approach maximum capacity, you end up with all the fans at or near 100%. So you don't really have any room to move them around. The optimizer can't really do much. So you end up with the same performance that way. But at these low loads, you can get a very significant amount of energy saved, which is very important specifically for this power plant because they're now operating in that realm a lot more than they're used to. So with this current mode of operation, this gives us a lot of room for savings. Over the course of the simulated year, we had 6.7% energy savings from this cooling tower, which translates directly into increasing the efficiency of this power plant. So just to kind of summarize our main contributions to this project here, we successfully developed a closed loop machine learning based optimization algorithm for a cooling tower that has a PID controller. As I mentioned, one of the key design elements here was to structure it in a way that we could preserve the original control structure without having to change it a lot. The idea is for this system to just kind of sit on top of or augment their existing controls with as little interference as possible. And if you need to, you can just simply turn it off and the cooling tower will continue to operate as normal. So something that could be done as hopefully as a relatively painless upgrade rather than a massive overhaul of the control logic in the cooling tower. Kind of digging through literature, this actually hasn't been done before, applying machine learning to control of a cooling tower. And it has a lot of applications beyond just cooling towers, we hope, being able to take advantage of extra degrees of freedom that might be a little beyond something an operator could do. No matter how well organized you are, trying to in real time keep track of 12 different values assigned to these cooling tower fans is just a little much for any kind of for a human or even just kind of an algorithm we've sat down and written out. But the machine learning can handle those nuances really well. So like I said, that hopefully translates to other systems that have similar complexity. The machine learning algorithm is pretty accurate, which is nice. We're happy to see a very high level of accuracy on predicting cooling tower performance, even when it didn't necessarily have all of the variables at its disposal. And this can be really helpful in an industrial or commercial setting where you're applying a machine learning algorithm, because let's say you don't have live temperature values for the value or the temperature outside, but you do have time and date values. So in the absence of perfect data, the neural network can still look for patterns and maybe learn it's generally cooler at night, warmer during the day, and do its best there. So it does really well with even if you don't have all the information you'd like to have. We determined there's no risk to the PID stability, maintains really good control of the tower, and that has priority over minimizing energy. And most significantly, the savings, like I said, are really significant at scale. We have 6.7% less energy over the course of a year on average. And if you look at just the low loads, you get an even higher value. So the more often the tower starts operating at these lower loads, which we presumably might happen more often over time, the more savings you end up getting through this. And this was done with practically no hardware upgrades. We determined the cooling tower there had pretty much all the sensors and equipment already set up. It just needed a little bit of, it just needed to have some extra software plugged into it to be able to do that. This work is currently published in the Journal of Cleaner Production. I have the reference right here if you're interested in reading more on that. But with that, I'll go ahead and thank you for your time and listening to this presentation, and love to open it up for some questions.
Thank you so much, Landon. So does anyone have any questions for him? So I have one. So you mentioned you used random data to initially train the neural network. So how would that apply to an actual system?
Oh, that's a really good question. So um, hopefully in a plant, you already have some data to work with. But even if you don't, um, a little trick that they used with the boiler, you don't want to necessarily start feeding random control inputs into your system. So you can actually put kind of guardrails on those values. Uh, so say if the cooling tower is normally all the fans are at 75%, when you're initially gathering data, you can give it maybe like a 5% buffer in each direction. So it can go anywhere between 70 and 80% to just kind of play around in there. And you can start with a really tight band on the decision variables as you collect initial data and then start to do closed loop control with the optimization. And then as you get more confident in the optimization actually doing a good job, you can start to walk out those boundaries, and you can effectively just kind of progressively implement more decision making authority in your optimization.
All right,
See
thanks
one
for
in the
that.
chat here
Yep.
from Alan here. How many plants use cooling towers in which this technology could be implemented? I don't actually know a ratio, but I do know these are pretty common in especially in drier climates like we are here in Utah. We do actually have someone on here, Jake Tuttle, who he's actually been now working at this plant. Maybe he has a little more of insight into maybe how common these are in other plants.
Can I answer that?
Oh, sure.
Yeah, so cooling towers. So this was a kind of a special assessment where we went to an actual power plant. So cooling towers would be pretty ubiquitous in power plants, but you also see them really commonly in manufacturing sites, which would be more traditional IAC assessment sites. One of the cool things about this project was, to my knowledge, this was the first time applying an application like this to cooling towers. So this, as Landon mentioned, this whole concept of using an AI-based model to model your system and then optimizing that model using a smart algorithm like particle swarm optimization really could be done on a variety of different systems. So it's really a function of the data that you have available and the control system that you can tie into at the plant. This software was originally designed to optimize combustion processes for power plants. And so this project was kind of a spin-off using that same software but applied to a new application, and it worked out really well.
Definitely. I think got our question in chat here from Joseph. How expensive is the machine learning capability? To clarify, you mean computationally expensive or like money expensive? Probably the latter. I guess it kind of depends who you go with. There's open source stuff that's actually free if you want to do your own thing. But, oh yeah, money. There's a lot of good free algorithms out there to do that. As far as out of the box stuff, I think that kind of depends on what company you go with, if they're going to contract for that. So, but the algorithms themselves are freely available. Lots of programming languages.
Hey.
Oh, Jake put a good note in here. This particular platform they're using at the plant is called Griffin AI Toolkit. He's got a link in the chat if you want to look more into that one. And they got pricing there on the website.
To answer Dr. Junker's question, it is quite expensive software. This was a large scale application, and what made this work for this kind of, I hate to call this a one-off application, but what made this work for our assessment was that the site already had a license to this software, so this was zero incremental cost. But so this is a nice area bridging the gap between application and research. So we tied this IAC assessment into an existing research project, and that is one of the reasons why we were able to have a successful project here. But I do think that in the not too distant future, we'll see more of these kinds of tools for the that would be more accessible to small and medium-sized manufacturers. So hopefully some of our smart IAC students from the program nationwide will see opportunities like this and start to develop software tools that could be cost competitive for small scale manufacturers.
Thanks.
I got our question from Hyun at LSU. Yes, is it usual for you and your team to collect this data set? It looks like a huge amount of data, and usually such data set is not available for IAC teams. Yeah, definitely at the smaller facilities, that it may be less common to have this much data, but at like a plant level, they hoard data like crazy. They have data for everything. So for this particular assessment, they were very kind in giving us access to that data for this project. Let's see, from Chandler, how difficult would it be to integrate this technology and by extension suggest using it? Implementation, there certainly is a bit of a difficulty there in getting it started. One of the nice things about using this ongoing is at least the software they had at the plant actually had the ability to just retrain itself. So it could just kind of self-manage. So as the cooling tower, as its performance degraded or for whatever reason started to, efficiencies change, things perform differently, the machine learning algorithm can collect more recent data and adapt to that. So you didn't necessarily have to have an operator on hand with a PhD in computer science. You just needed someone to help set it up, and I think they have a contract for tech support when they need it, but it runs pretty well just once you get it going.
I would also like to answer that question more from an AR point of view for all the IAC students and teams on there. This was definitely kind of a one-off thing. We thought this was just a cool opportunity. This started out as an IAC research project. So it was this really nice hybrid between something that was interesting research project, but also something that had real world applicability. But we were uniquely positioned to have tied into an existing software license and an existing research project on the combustion optimization side of things. So as far as making this like a bread and butter AR, I don't think we're there yet, but I think there's definitely business opportunity there. If you do find opportunities to optimize a big process, so if there is a process that has a lot of data available and they have a really good control system, then there may be other software products out there that can do similar things. So for example, we have recommended installing something called model predictive control at plant sites before, where we see that there are some big savings opportunities associated with just better automating your process. So if you searched for vendors doing model predictive control, you would certainly be able to find some. There are other vendors doing something called real-time optimization. So I would say this project falls under that category. So if you did evaluate a big process that you think meets these criteria, and you think that it does take a lot of manpower to get a project like this going, so the bang for the buck has to be there. But I'd encourage you to search for vendors using the keywords real-time optimization or model predictive control, and that might help develop some leads for vendors that could possibly come in and do real installations, because those types of technologies are becoming more and more applicable, especially in like chemical processing industries.
Hi, this is Jake Tuttlette. Also, just want to hurry and comment on that. I worked with Landon on this project and did a lot of work on site. We actually did implement this and use it in closed loop at the power plant. And over the course of, 6 weeks, 3 of those being with the technology active, and then a trial or a comparison period of 3 weeks, we saw 5% savings in energy use. Relatively simple to implement, partly because the software is already in place. But the application development and integration into the system honestly was pretty simple. And the plant was very easy to work with once they saw the information that Landon just presented, and then the performance of the overall system.
Definitely. I think Kedar from University of Massachusetts. I think you were trying to talk a moment ago. Do you have a question?
Yeah, thanks. I just put it in the chat. My question was like really simplistic.
Okay.
I understood that the training data comes from, the training data for the fan speed comes from the PID algorithm. And so I was just wondering, how do you prevent the network from mimicking the PID algorithm? Since you want to go towards a better algorithm, as I understand the project.
Yeah, so we had to do some thinking to make sure they the two didn't end up fighting each other, because the PID controller was trying to control the temperature set point, where the optimization algorithm was trying to minimize power. So our worst case scenario ahead was like, what if the optimization just decides to try and turn all the fans off because that's the most efficient thing to do. So so we don't want that to happen, and it did, unfortunately, with the structure we set up, because the machine learning never sees the PID value, and we only fed it data at steady state. So this cooling tower hit steady state pretty quickly, and we ran the optimization at a lower frequency than the PID controller. So optimization learned to kind of like predict where the PID would be, and be like, based on where that PID is going to be based on these inputs, it would figure out the offset values. And then we leave that alone for a little bit while the PID kind of chased it and settled out. So,
Okay. Thank you.
But yeah, so this is purely a steady, this is jumping between different steady state operation points rather than trying to deal with the dynamics in between it.
Okay, thank you. Yeah.
Gotcha. Oh, I just realized you had your hand up, Swarup from UF. It looks like you posted in the chat too. What are the benefits of using neural networks over MPC? I guess so the machine learning has a lot of different stuff, but in this particular way we used it, the neural network was just a model. And so I suppose you could use them for some form of model predictive control. The thing that the neural network really replaces is like a first principles model to be able to predict what your system will do. And those can be really difficult to piece together because you have to, they're kind of unique to each project and they require a lot of manpower. And then when the system starts to behave differently, you have to refit everything. Whereas the neural network just kind of does that by itself from a data-driven perspective. So I guess maybe to answer that, one of the main benefits is you don't need to do a first principles model. And depending on how your MPC is set up, you might even be able to do some predictive control with this as the model. Although we were just doing steady state optimization here for this project.
I have a question. Besides the challenge that you were addressing about the neural network algorithm overshadowing the PID loop, what other challenges did you guys anticipate and is still continue to worry about it now that you've kind of implemented and see the energy savings?
I guess one of the main worries with neural networks is what happens when it enters a realm that's never seen before. Will it behave like really sporadically or something? The neural networks, they don't extrapolate well into territory that they've never experienced some data in the vicinity. So I guess that was a main concern. This particular software, I think, has some checks you can program in there to keep it from trying to do anything too ridiculous. And it has just, I think, a fail-safe to just kind of fall back onto either a previous optimized prediction, or even, I think in a more extreme case, even just shut off, since the plant can run fine without the software. So I guess I don't know if there's much that, terrifies us about things going wrong, because it's got some fail-safes built in there. But as far as losing energy savings that are unnecessary, that would be one of the big ones, is what happens when we get to a realm we've never been. But fortunately, since we're always collecting data, if it gets to a point where it starts making some bad predictions and some suboptimal decisions, we can feed that into the next training round, and hopefully it performs better in that area. So we noticed on the, I guess one thing neat we found is when we were doing that iterative training process, we started with random data, trained a model, put it in closed loop, generated more data, trained the model, generate data, and back and forth. It really honed in pretty quickly on an accurate model, because if there were points in the model that it tended to over predict what it thought it could do, we ended up getting a lot more data in that area. So the next model actually predicted that area more accurately.
Just curious how you toggle between just keeping that algorithm on versus going back to the PID controlled approach.
Sorry, like how to know when to not trust the algorithm or when to back off. Maybe Jake has some more insight to this. I know they have some guardrails on what acceptable system inputs are.
Yeah, I can definitely comment on that. Sorry, Cody.
Oh, sorry. I just wanted to say, you always build in like an operator on-off switch. So if the operator senses something weird, they can always just switch it off, and it will just go into, the application would still be able to collect data, but the operator can turn that off. But also, Jake and Landon, who really had a big hands in kind of designing how this thing would work, you try to set it up so that, and I think Landon explained this a little bit, but you set it up so that they can work harmoniously together. So the PID loop is still determining sort of total fan power that you need. It's giving the overall value you'd need to keep your cooling tower at the right set point. And then what the optimizer does is it says, okay, well, I'm going to do this % on this fan and this % on this fan and this % on this fan. So the PID is still there for control purposes and reliability purposes. And then the optimizer is really just figuring out how do you distribute that load among all the different fans. Go ahead, Jake. Jake knows this better than I do. So if you have anything to add, Jake, chime in, please.
No, you pretty well covered it. The only thing I would add is the on-off switch for the operators. These operators, they are experts in everything that they do. They know the power plan and performance and everything better than the back of their hands. And so they have complete control when something doesn't appear to be correct to turn it off. And in our implementation, we worked very closely with them to develop the type of performance they would expect, which went through a few iterations of developing the control scheme. But ultimately, the operators are in control. So if something doesn't appear right, they would usually turn it off. But we also did develop fail-safes of, if we're operating at 75% speed and a fan all of a sudden wants to go to 0, we would trip the system back to pure DCS control, knowing that something wasn't right, and allow us to review what had happened and then correct the situation, which, I will say happened, I don't think ever happened, but we did build that into the system.
So anyone have any more questions? All right, so thank you, Landon and Cody and Jake, for your presentation. And as a reminder, our next webinar will be in 2 weeks. Thank you, everyone, for attending.
Thanks, Landon. Thanks, everybody, for having us.
Yeah, thanks for coming.
Interesting presentation. Thanks.